All right, so now we're looking at parametric equations. Okay, so let's not be too worried about the what it means by being parametric equation. Let's start out with something like this. So how about I'm going to start out with just sum two function. Now remember, keep in mind it's just sum two functions. They don't have to have any relationship yet, and we don't need to worry about the relationship between them. So how about some function? I name them now. Also throughout the whole time we're learning, and I've been using f of x or g of x or h of x, but now the function's name here that is x, and x takes the input t. So here, how about one function is defined as 2t plus 1. So the function is just a usual function. The function's name is here. We named the function x, and the input variable is t. So what this function says is when, for example, when t equals 1, for example, right, then 2 times 1 plus 1, and then that gives you the output. Okay, so we got one function, and the rule of the function is here. Now, let's name another function. How about y of t? So y, we've been so familiar with y being, the y coordinates or y as a function of x, but here y is a function of t. Okay, y as a variable, it's the name of our function, and y of t here is a function. How about let's call that, so I had on my lecture note here 3t minus 1. Okay, so these are just some two separate functions, nothing related, just some two functions. One function is the x function, one function is the y function, and they're both in terms of t, the t variable. Okay, and so now this is what I can see right here. The idea now is that we call these two, now x equals something, this is one equation, x equals 2t plus 1, and y equals 3t minus 1. These are obviously two equations. Let's do a common table of values. Now, in our usual understanding, the table of values go, the input variable is the t variable. One more thing I need to mention, how about the t variable here is, how about one common variable? So whatever the input variable that we assign for the t right here, let's say t equals to a value 5, for example. That same input value is going to be responsible for the output value for the two functions separately. And you will see exactly what I mean when I'm going through the table here. And so what I was about to say earlier, let's say we have one column here for the input variable values. And then the x of t, as usual, is here. So just the idea about table of values as usual. How about we go with, let me start out kind of down here, t equals 1. When t equals 1, okay, x of t, the function here, 2 times 1 plus 1, so 2 times 1 plus 1 gives me a 3. That's the output for this function x. But now the idea is, as I said earlier, one value for our input variable t, we can use that for two different equations here. So how about I'm going to extend the same table we've been knowing it since pre-calculus 1. The same table we've been knowing it, now we extend that to one more column. So the same t value here, it's also responsible for changing the output value for our y function right here. And the formula is right here. And so anyone can quickly do a calculation right there on that. Okay? And so the calculation that come out from here, when t equals 1, right, according to that rule right here, and we're looking at 3 times 1 minus 1, that's 2. So when t equals 1, x equals 3, and at the same time the function y equals 2. Okay? And so we can keep doing that for a few more values of x, just to have some good time with that. Okay? So when t equals 2, for example, all right, then once again for x, when t equals 2, 2 times 2 is 4, right, plus 1, that's 5, right, and then this one here, when t equals 2, the y value, the output value on our y function, now it comes out being 5 as well, because 2 times 3, right, 2 times 3 minus 1, okay, and then we can try that for when t equals 3, okay, x value comes out being, that's 2 times 3, making 6, plus 1, 7. Okay, and right here we're looking at 8, right? 3 times 3 minus 1. And then we can also go with negative value for t. And how about 0 for our value for t? So the t variable, again, recall yourself as far as our understanding in terms of function, the t here is the independent variable. So in that way, okay, when t equals 0, we can pick any values for t here independently. And then the x and the y values will come out dependent on the value for t. And so once again, I have to emphasize that t is one common input, but once we have one input for t, we come out with two different values, one for x, one for y. Okay? And so when t equals 0, just like that, right? Now x equals 1 and t equals negative 1. And just like back to what I said earlier, t can also be negative. So how about let me pick independently t equals negative 1. So that gives me minus 1 for x and minus 4 for y. Okay. All right. And so the idea now is that when we're working with two functions but share the same common variable like that, right? These two equations here, I said earlier, each one of these, even though I call them a function, I call any one of them a function, but in the end, each one of these is an equation. So together, these two are, right? We have what we come together here is a system, right? It's a system of, these are parametric equations. And let me write that in red ink. And so these are parametric equations. All right. So that's just, now I'm introducing it, so I'm just listing down the two functions. But now when it comes to parametric equations, a lot of time people write things like that. It's a system of two equations. One equation is x as a function of t. Okay? It depends on the common variable t as 2t plus 1. And then the other function. So first, most ultimately, it's just two separate functions, but both dependent on the same input variable t. That's the idea about parametric equations. And then here, y of t is 3t minus 1. This is the way how we will see it's written more commonly right here. Two equations written down like that with curly braces. It's a system of two equations. And at our level here, we're only at the pre-calculus 2 level, and being introduced for maybe the first time to parametric equations. Then our parametric equations, the set of parametric equations, only usually involve just two equations. But be ready for that. There may be even more, right? There's x, y, and z, and many other parametric equations in one system of parametric equations like that. So here we primarily just look at two. Okay, and so that's ultimately the idea here. Now, what's useful about this? What's useful about parametric equations that we have to learn? So now think about the idea as following. Yes, we used to know that in a graphing space, okay, in a graphing space that we used to know, then x-axis, y-axis, and we used to know from pre-calculus 1, and up until any time prior to this point right here, then we used to know that y is written as a function f in terms of x. And so we have been referring to x here as the input, the independent input variable, and y as the dependent output variable. And then from that point, see, throughout our whole class so far, and we've been investigating functions up and down right here. But so that's because we have a rule, right? Y as an output equals the function equals a function in terms of x right here. So we choose x independently, and then x gives a value, okay, on the graph right here. And then that now as being a point, it's just x comma y. Okay. So that's how we have been knowing so comfortably. But now at this point, the idea is, let's forget about the relationship we used to know. So what I just now erased, the relationship I've been talking about is the relationship that y, the vertical value, is treated as a function of x. But now just think about the same graph, or maybe let me draw even a different graph right here. in the end, you can draw various shapes right here. I mean, we can draw so many different various shapes out there. This is a graph. It's a drawing. And then anywhere, any point on that graph, once again, any point on that graph is a combination of two values, x and y. But then, so now think about it. X and y can be two independent values that make up a point. So x and y, we treat them as the x coordinates and y as the y coordinates. But now the idea of parametric equations, the usefulness of parametric equation is that the variable t right here is responsible for being at different points. So let's say when we're at this point right here, it's a different x value and a different y value because a different t variable is responsible for that position on the graph. Okay, so that's the idea about parametric equation. So we use the parameter t right here, okay, to be responsible for changing. So now we only see x and y here as two variables that are completely independent from each other, and they are both dependent on t. So t is the parameter, the value that's responsible for changing the x and y value for that point. So at a different t value, we're here, and at a different t value, we're at here at that point. And so let's say right here, that point on the graph, there's it's another pair of x and y. Okay, it's another pair of x and y. And so once again, we don't know, I didn't write down the rule yet, but there has to be some other t values that's responsible for putting our points right here at that spot, at that coordinates x and y. All right, and so that's the first usefulness of using parametric equations right here. So back on this board when I was writing this, so now we can see that I used that term earlier. T, let's call the parameter. All right, and that's how we're seeing it. So how about let's do a quick demonstration example right here, and we want to plot, we want to put these on the graph, and to make it consistent with what I was saying about this idea right here, that different t value put our point at different, put different t value, put ourselves here at or put us into different points on the graph right here. Different t value, right? Put a point at that specific coordinate. So we want to find out. Now the demonstration I'm about to show through the example is not necessarily giving a wavy curve like this, this nice bent waving curve, but the idea demonstrates the same exactly idea right here, that different t value put ourselves at different point with coordinates x, y, and so each one of the x and y coordinates of the point is being determined by the parameter t. All right. So I'm going to turn over to my graphing space on the computer screen right here. All right. So here we are here with I'm using decimals for this, but see. So I'm going to define some two functions x, right? Now it's just a limitation with the software that I'm using here, with the program, the web program I'm using here, that I cannot use directly the variable t. So I have to define an intermediate function that I call f sub x, right? X of f of x equals 2x plus 1. So x of f right here is the function's name, and then y sub f is another function name. So this is sort of like x of t and y of t, and this is 2x plus 1, or on the board earlier it was 2t plus 1. And then here it's 3x minus 1. It's just the way how we have to use it to operate with that on the machine, but it's really was the 3t minus 1. And so now the table of value was here. On the table of values on the board earlier, I was putting down -1 for t. And so it came out with these values that's exactly consistent with what we saw earlier on the board. And then now on the next one here, okay. And now I hope you notice already that as I put in, now let's roll back to the beginning point right here. Now as I put in that point, now when t equals -1, see, it puts a point right here, because when t equals -1, we have a point that sits right at x coordinates being -1 and y coordinates being -4, which is this point right here. All right. So the point right here is making it clear that see, it's a point we are being placed, we are placed at that point, at that position with coordinates see -1, -4, where it's the t value, the t parameter that's responsible for that is being assigned with value -1. Okay, and so now I'm gonna move on right here. On my board earlier, I put down 0 for t. So we come out, so now we are placed at that next point, at another point where this point is 1, -1. 1, -1. It's right here. Okay, and now I'm going to continue to grow my table of values right here. So with technology, we should be able to do this a lot faster than on the board earlier, on the whiteboard. So now when t equals 1, so we are placed now at the point where x equals 3 and y equals 2, just consistent with the what's on the board. But on the board, I was doing that simply just as a calculation to show you, the usual table of values idea. But now, graphically speaking, when t equals 1, we are put right at, our point is put right at that position, 3, 2. So think about the point now is as t changes, see t equals 0 is here, t equals -1 is here, t equals 0 is here, t equals 1 is here. So as t steadily increasing, these point changes positions. Okay, and then let's continue to explore where else our values change to, our points change to. So when t equals 2, we got 5, 5, just like how it was on the board. And when t equals 3, okay, we have another point that popped out. So now, see, the idea now is that as we put in those values, right, and now with the software, let me zoom it in, let me zoom it out right here. And with the software, I can grow this table a lot longer so that we can start seeing a trace. So now the trace of these points. So on the graph, of course, it won't show, we will never have to show the values for t, but these are the values for x, y, x, y. See, these are all x, y. Okay, but then we are placed at different values. Okay, so now as t increases, observe my table on the left-hand side right here. As t increases, right, we keep having more points that popped out, and so it looks like. So that usefulness I'm talking about is as we increase t right there, and we will never show t on the graph directly, but as we keep increasing the value for t right here, then we see that the point being changed. The point being changed, it also shows the direction of the change. It also shows the directions of where the points are moving. So back on the graph, think about the motion of the points right there. Okay, I'm gonna roll back to this beginning point. Right here, when t equals -1, we are at that point. Okay, that point. And then now 0, okay, see, think about the point is moved or is repositioned from here to here. Okay, and then we can think about, okay, when t equals 1, we have that. So think about if we sketch the picture, if we sketch a graph following this order, if we're sketching a graph following this order, then it starts here at that point, and it goes, and we sketch through that point, and then we sketch through that point. Okay, and then we keep, see, the direction, there's a direction of the sketch of the graph right there. Okay, and so back to what I was saying, the idea now is that we're not only just seeing we are being placed at different points, but it also has the directions indicated, the direction that once we created the curve, see, the same curve, the same drawing, but is it either we are starting here and going along that way, or it matters that we start here going along that way. Okay, so we may even have different parameterizations, different setup, the parametric equation that describe the same graph as well, because the parametric equation is not only showing the position, okay, but it's also responsible for us to see how these point changes as a directions. It shows the directions of change, okay, along our graph, our path like that. Okay, and so now let me get back on the graph right here. And let me show this final one right here that you can see. So let me now just simply put in. Okay, you don't need to know how to do this yet, but it will come. It will come. But right now, allow me to cheat around a little bit. The point now is that I want to think about if we put infinitely many t values here, then all these points here will come to a specific, will give a specific shape that we call the graph, and you have already recognized some shape of the graph like that. So let me play around with. Let me show this right here. All right. So the line I just now put in, right, and please don't worry about the equation I use here right here, but So now after we plot all of the points, okay, in greens here, after we have plotted all of the points in greens, then we recognize that these points line up into a line, and that line I just now showed to make it clear that all of these points line up in a line. Okay, so because we only reach to these t values being a whole values, but what about other t values like a t equals 2.5? Okay, right here, 2.5, right? We have another point if you observe right here. The table shows 6, 6.5, which is that point right there. Okay, and then between 2 and 2.5, if you put in a 2.25, for example, you have another point right here. Okay, so the idea now is that we have infinitely many points, and any point, as long as any point that comes out from any point that's being determined x and y value, any points where x and y values are being determined by this set of parametric equation should lie on this particular line right here, should give the graph being this line right here. And that's the idea about we're plotting parametric equation, and the plotting a parametric equation eventually give us a particular graph right here, a particular graph for our work. All right. And so in that way, on the board, now let's just look at one example. And using technology is only one way. Okay, using technology is only one way, and you can see that my technology, I try to run it as closely as if we were doing that by hand with a hand sketch. So it's completely fine doing a table of values manually, right? Writing a table of values, and then we sketch the graph. All right, so let's call that example 1. Okay, so that's our wording of the problem right there. So let's write it down right here. So how about x of t? We got, okay, that's our system of parametric equations. Okay. All right, so I hope you have had enough time writing it down right here. So this is how we're sketching it. Okay, and assuming that you already had a good record of what the equations are. So we're starting out plotting. So we're starting out with the table of values. Okay, so one column for the value for t, because remember now these two equations are parametric. Okay, so they share, even though x and y, so x, think about this is x coordinates of some point, this is y coordinates of some point, and both coordinates here are values that depend on the same input, the same parameter t. That's the idea. So in that way, I'm going to sketch one column for t. I'm going to put in another column for the values of x as we change to different values for t, and one column for the value of y. Okay, so now we can go. Okay, we can go with a few negative values. How about negative 3, negative 2, okay, negative 1, and then 0, and then let's go successively a few other values like that. Okay, 0, 1, 2, and 3. Right? Just for all of that. All right, and so now we can easily do this. Right? Then, so when t equals negative 3 right there, we got minus 12, and t equals negative 3, we're looking at negative 9 for y, negative 2 right here, and you guys, any one of you guys can do the independent work as well, and to go along with this. So minus 2 right here for t, right? When t equals negative 2 independently, then x here will come out being negative 7, okay? And here we having another negative 7. Now for t equals negative 1 right here, we're looking at negative 2, and here is going to be a negative 5, okay? And now when t equals to 0, we're looking at 3 for x and negative 3 for y. And when t equals 1, we're looking at 8 for x and negative 1 for y, okay? And so on and so on. And then 2, okay? Here we have 13 for x, right? And 1 for y, okay? And then when it's 3 right here, we're looking at 18, and we're looking at 3 for y. All right, so those are the values, and we can keep going further with the table, and you can even try with some values between 0 and 1 or between 1 and 2 right there. There should be infinitely many values for t that you can try for that, for these. Okay, so now let's see how we can do that on the graph right here, on the graphing space right here. I mean, if we're doing that with the technology. Okay, so the most important thing, I'm going to delete out my table. Okay, and this line is now no longer applicable. And I'll get to that kind of problem where we're going to learn how we can get to that line. Now, for x right here, we're going to need to adjust this. So now it's going to be 5, but don't type 5t here, 5x plus 3. Okay, and here I'm going to go with 2t minus 3. 2, so 2x minus 3. All right, and then so now we're ready for confirming. So I'm using this just to confirm. So negative 3 was the start. We got minus 12 for x and minus 9 for y, which is consistent with what we had on the board earlier. Now minus 2, okay, negative 7 for xy, okay, negative 1, and it comes out with these. 0, right, and now we can keep checking. And so now as we go along, you can start seeing these points that popped out right here. Right? So let me roll back a little bit. Minus 3, we stayed right at that point. See, minus 12, minus 9. And then we came to minus 2 for t. There's another point that popped out. So it looks like the graph goes this way. The graph will go this way, but 2 points is not good enough to see the complete picture of the graph. So how about another point? Right, so negative 1, so we got another point right here. So the point seems to be heading in that direction. Starting here, it goes along that way, and only 3 points is not telling much of the story. So t equals 0, we got another point that popped out right here. Okay, and that's what it meant by plotting right there. Okay, and then 1, and then 2, and then 3. Now you're seeing the points popping out right there. All right. And so just like that, see, if I wish I had more board space right here, but that's how we're doing it. Right, x and y axis right here, right? First point right here, so now we just write minus 12, right? Negative 9, so how about right here is negative 12, so negative 6 is about right here, right? A third of each of these is a third, that's negative 2 right there. Okay, all right, fair enough. And then negative 6 and negative 9 on the y-axis, right? Just about down here, see, we got a point, right? And then, so that point right here is equivalent to t equals negative 3. See, so when we're doing that with paper, then we have our freedom to make the label for the corresponding t value, but this is not really how we put the t value on the graph. The graph can only show x value and y value as a pair. So this pair right here is at negative 12, comma negative 9 right here. See, negative 12, comma negative 9, and these two values came out from the table of values. And so the graph was kind of going like this, and of course I'm off scale, but so the next one here was negative 7, right? Negative 7 and negative 7, right? So it's kind of like down here, right? And that's why we got another point right here. This is equivalent to t equals negative 2. So we got 2 points. And then the next one here, minus 2, right? Minus 2 and negative 5, so it's a little bit up, right? So we got that point right here, right? And of course now forgive me that I'm off scale or anything like that, but that point is equivalent to t equals negative 1. Okay, and so now, see, the problem was asking us to plot, so that's what we did. We constructed a table of values. That's the usual thing. And then as we got the table of values, these are the points that we're putting on the graph, right? We don't put the point for t. We put the point for x and y as a point, coordinates point. And then after we put in enough points and got tired of doing that, right? Then we have a plot, right? And the further we go, the more complete our plot is. So that's plotting. And now the next part of the problem of the example is asking us to sketch the graph, right? So now after having the plotted points put down on the graph right here, we're going to go to just connect the points, connect to the point through whatever shape that these points define. All right, so that's how, so this is the graph that we have sketched, okay? And on machine, now with using machines right there, okay, so the idea is to use straight edge to get that, right? But I'm gonna, for machine, it doesn't know how to put in a straight edge, so I'm gonna have to come up with some equation that put a line right through these points right here. And then we will learn, again, I promise that you will learn how to come up with these equations. All right. But let's say now we have all right, so here's our line like that. All right, so this line, as we sketch through the points, we have created a line, and this line right here is the graph for our parametric equations, for our system of parametric equations. All right. And so that's the idea about how we once we're given a set of parametric equations, a system of parametric equations, then we're able to plot and sketch the graph. So that's the first basic skill of what we're doing with that. Okay, so let's head into the next understanding. So now let's head into the next understanding regarding the parametric equations. Okay, and so now again I'm going to roll back to the two equations that I initially put in. So x of t was a 2t plus 1 and y of t 3t minus 1. Okay, so we have a set of parametric equations. This is the one I put it up earlier. So now again, there are so many various different ways of writing it, right? So we can write it as x is 2t plus 1. So x equals, and sometimes you can even skip the t right here. Okay? And then y equals 3t minus 1. And as a matter of fact, just like what I said, we can skip the t right here. So how about I'm going to purposely skip the t, because the t is just to precisely indicate what parameter value responsible for changing x and y, but in the end these are all variables and variables, right? T is a common variable, and x and y are all two other variables that both dependent on t. Okay, so from that system, this is what I see right here. All right, so that's just two different ways of writing it, but from the way how I'm seeing it, if x equals 2t plus 1, because right now in the way how the system is written, then we are writing as two equations, and x is a function dependent on t, and y has a relationship in terms of t, with t. And it shows nothing relating between x and y. X and y has no relationship recognized. I'm not saying that they don't have relationship. I'm just saying that x and y currently have no recognized relationship, and we are about to find that. So back on this work right here, think about x equals 2t plus 1. So if x equals 2t plus 1, now we've all learned, this lesson here we're learning is supposedly after the pre-calculus one, so you're familiar enough with all of the algebraic manipulation of our work right here. So I'm going to subtract 1 from both sides, making it x minus 1 equals 2t, and then I'm dividing both sides by 2. Okay, that making it, you can write it, that's making it x minus 1 over 2 to equals t. Or you can, so when it comes to this point, you can also write t equals, and then you can turn this into two separate terms, right? 1/2 x minus 1/2. That's just different ways of how you want to write it, but these are just fine. We have basically solved for t, right, in terms of x, right from that first parametric equation. Then we solve for t in terms of x. Okay, I'm going to do the same for the other equation. So how about, see, y of t is 3t minus 1, and for short we just write that y equals 3t minus 1. And so now I'm doing the similar thing. I'm going to solve for t here. So I'm adding 1 from both sides, to both sides. So y plus 1 equals 3t, and I'm dividing both sides by 3. And I'm looking at y plus 1 over 3 equals t, because the 3 here got cancelled. Just like that, back here, the 2 was cancelled. So I have solved for t as an expression in terms of y, or I can optionally go 1/3 y plus 1/3 equals t. All right, so the point now is that, see, at this point, what's important to recognize is that t at the same time equals to this expression, x minus 1 all over 2. And at the same time, t equals y plus 1 over 3. And so now we can do the following. X minus 1 for sure over 2 has to equal y plus 1 over 3, because these are both equal to t. All right. So that's just some algebraic manipulation around the work right here. But then in the end, what we have realized now is that from our system of parametric equations, we have brought to our final relationship. This final equation here only relates between x and y. Okay, so this equation now only has x and y variables involved, no more t involved in here. All right, so the work we have just done here, we have gone from parametric equations. That's the starting point. Okay, we start with parametric equations. Okay, and then we ended up, right? And then we ended at this equation here only involves the two variables x and y. We refer to this as Cartesian, okay, equation. Okay, and that's just one equation. Now, when it comes to Cartesian equation, that's just only one equation. You may rearrange, you may algebraically rearrange that equation. That's not a problem, but it's still a Cartesian and the only Cartesian equation out of this set of parametric equations. And then another way of calling that, this is instead of calling that Cartesian equation, people can also call that rectangular. Okay, and you have learned this term in other lessons, rectangular coordinates. If anyone has learned about, if we've learned about polar coordinates, then we have seen these terms before as well, rectangular coordinates. All right. So that's how we are. So in this example right here, primarily the idea here is that I was converting from starting parametric equation in this demonstration activity, and then we made our way down. The essential theme here is to solve each one of these parametric equations here, solve for those in terms of t, solve for t from those equations in terms of x and y, and then at the final step we equate the two expressions of x and y together, and we come to that final equation we call the Cartesian equation. All right. All right, so now let's call that another example right here. I can call that example 2 right here, so that we finalize our scale right here. Okay. And y of t equals 2t minus 3. We want to convert that set of parametric equations to Cartesian. Okay. Cartesian equation. Okay, and the idea of the Cartesian equation is these have rectangular coordinates. All right, so that's how that's what's instructed in this example. So now the work is done quite trivial, and it's just like how I was doing that earlier demonstration. So we're starting out as the foremost step right here. We're starting out with letting x right here, right? And we can skip that of t notation right here. So x equals 5t plus 3. Okay, and then so from that we can solve for t right here. We can solve for t in terms of x. So I'm subtracting 3 from both sides, making it x minus 3 equals 5t. Right, that's just the algebra. And then we're going to divide both sides here by 5, right, giving it, and then the 5 got canceled. So that's now in the next step, it's making it t equals x minus 3 all over 5. Right, so t equals x minus 3 all over 5. Or you can rewrite it. There are so many ways to rewrite it. You can also write it t equals 1/5 x minus 3/5. I decided to just stay right there. The same way with the other equation. Okay, so y equals 2t minus 3. Now I'm adding that 3 to the other side. Okay, so making it y plus 3, right, equals 2t. That's what I did after adding 3 from both sides. Now we're going to divide by 2 on both sides. We're looking now at, and the 2 got canceled. So now we're looking at t equals y plus 3 over 2. And so now once we have solved both equations for t, then we're going to just simply set x. Okay, so the third step right here, the x minus 3 over 5, that was supposed to equal 3. And so now, but t is also, so that was supposed to equal t, and t is also equal to the y plus 3 over 2. So now that means these two expressions, which only involves x and y, have to equal each other. 5 plus y plus 3 over 2. And this equation now is completely free as a check right here. we're completely free from the t variable. So here there was x, y, and t involved, but here only x and y involved. This is now, it brings a perfect sign. It's saying that we are right here at our Cartesian equation. All right.